You can also do chemical analysis based on quantity, i.e. how much you have going in. And this is a real common kind of procedure in chemistry, and we will do it this quarter as well. So quantitative analysis is just a way to determine the amount or the concentration of a substance in a mixture. And usually these kind of methods use what's called a titration. And titrations are a super cool tool used by chemists to figure out a lot of information. Now in a titration, you use what's called a burette. Burette's that long, skinny, narrow tube right there in the picture. And you fill it up usually with something of a known concentration, like a base or an acid or who knows what it is. But usually you know what's in there. And the burette allows you to add very highly well-known amounts, like volumes, into an unknown solution, which is called the analyte. And they're real powerful tools. You can get really good results. You're usually looking for what's called the equivalence point, where the moles of what you add equal the moles of what you started with, or in this case, the moles of the titrant from the burette equal the moles of the analyte that's down there in the base. Sometimes they'll use an indicator, which is a substance that changes color when you get to a specific amount in the titration, which is cool. This is something we will do. We'll do more of it in Chemistry 223 probably than Chem 222, but it's used by chemists a lot of the times, and it's a very powerful technique. So let's see how chemists would use this technique. This is an example where we have hydrochloric acid, HCl, reacting with sodium hydroxide. That's an acid and a base, a strong acid and a strong base for that matter. And like all acid-base reactions, you end up making water, which is a liquid, and some kind of salt. Salt is just the product of an acid-base reaction. So in this case, because the Na plus and the H plus are trading places, you end up making HOH, which is water, and NaCl, so NaCl is the salt. So in this problem, we have a 50 milliliter sample of aqueous HCl, and we don't know what concentration it is, but we're going to titrate it with 35.23 milliliters of a 0.250 molar sodium hydroxide solution. Now, the big M is molarity, which is moles per liter. And moles per liter, you can use that and the liters, 35.23 milliliters converted into liters, 1,000 milliliters per liter. We can use that and a mole-to-mole ratio from the balanced reaction to end up finding what the concentration of the HCl is. So in this problem, we are after the molarity, the moles per liter of hydrochloric acid. And believe it or not, we have everything we need to make this happen. So key to this is the balanced reaction. It says 1 mole of HCl is needed for every 1 mole of NaOH. So we're going to find the moles of NaOH. It's going to equal the moles of HCl, and we're going to divide by the volume in liters of the HCl that we had. So let's see what this looks like. This first part here, we're taking the milliliters of sodium hydroxide and turning it into liters. 1,000 milliliters per liter is the game we'll play a lot in these sections. And then 0.250 m, 0.250 moles per liter, we'll multiply the volume in liters by moles per liter to get moles. And then the balanced reaction up there, like I said, mole of NaOH takes 1 mole of HCl. This is going to be 8.81 times 10 to the minus 3 moles of HCl. So because the sodium hydroxide was needed to get to that point, that's where we got the moles of HCl. And finally, moles of HCl divided by the liters of HCl, 50 divided by 1,000, 0.05000 liters, 0.176 moles per liter. That's the molarity of our hydrochloric acid solution. So if you forget what the concentration was, or the label falls off, or you accidentally add water, etc., you can use sodium hydroxide like this to figure out what the concentration is, which is pretty cool for chemists. Another type of quantitative analysis called gravimetric, and this usually involves the measuring of so much mass in grams of a chemical change. It's usually a precipitation reaction, but it does sometimes kind of vary. And you can usually You can usually filter the precipitate, so you'll have a solid and some liquid, and you can filter then the solid out to collect the solid by itself, and you can dry it under some kind of a vacuum or under a heat lamp, something like that. This is an example where they're taking a sodium sulfate solution on the left and adding some barium chloride, which is also a solution on the right. And you're going to add the barium and the sulfate together. And if you remember from the solubility rules, barium sulfate is very insoluble. It's not an AQ, it makes a solid, a precipitate. So this is a precipitation reaction. Barium chloride and sodium sulfate are making barium sulfate and sodium chloride. But it's the barium sulfate here which is interesting. It's very insoluble. So if you filter the solution, the solid will stay in that little piece of paper at the top of the funnel while the liquid goes through. You can then measure the amount of barium sulfate collected and do different things from there. So it's usually some kind of precipitation reaction followed by filtration. Sometimes there's other methods, but it's a pretty nice way to do it. This is an example of how this works out. So let's say we have a 0.4550 gram mixture. Mixture means impure, by the way. But our mixture does have magnesium sulfate. And like we just talked about, sulfate and barium make a solid. So let's say we dissolve our unknown mixture in water. We treat it with a source of barium ions, barium nitrate. And at the end of the day, we end up with 0.6168 grams of barium sulfate. Well, we can use all of this information to find the mass percent of magnesium sulfate in the mixture. So just like you can find, for example, percent potassium chlorate in a mixture, in this problem we're going to find percent magnesium sulfate in the mixture. And we're going to use the precipitation of barium sulfate to figure this out. So what we'll do here is we'll take grams of barium sulfate and turn them into moles of barium sulfate. There's 1-to-1 stoichiometric ratio between BaSO4 and MgSO4. So moles BaSO4 equal moles MgSO4. And finally, you can multiply by the molar mass of MgSO4 to find the pure grams of MgSO4. And I will just about guarantee that it's going to be less than 0.4550 grams, because that's a mixture. It's not pure magnesium sulfate. So the percent magnesium sulfate will be the grams of the pure MgSO4 that we calculated based on barium sulfate. We'll divide it by 0.4550 grams, multiply by 100. Good to go. So let's see what the math looks like. So at this step, we're turning grams of barium sulfate collected into grams of magnesium sulfate in the original mixture. Grams to moles to moles to grams. So grams to moles, molar mass barium sulfate 233.43. The reaction says 1 BaSO4 is collected for every 1 MgSO4 that was present, 1-to-1. We'll then multiply that by the molar mass MgSO4, 120.37 grams per mole. There were 0.3181 grams magnesium sulfate in our original mixture. But our original mixture was 0.4550 grams. So the mass percent will be the good stuff divided by the total times 100% basically. 0.3181 divided by 0.4550 times 100, 69.91%. So our sample is 69.91% magnesium sulfate. And we've got roughly 30% of something else. Who knows? Hard to say at this point what something else is, but we at least know the percentage, the purity of our sample, and that can be kind of cool for chemists. Another way to find out what's inside your sample is to do what's called a combustion analysis. And these are kind of fun because you get to burn things. And usually this combustion analysis is used for organic materials, things with carbon and hydrogen, sometimes oxygen. In reality, though, you can use just about anything because a lot of things will quote unquote burn, even though you may not think they will, but the organic parts are pretty cool. So in organic chemistry and biochemistry, this method is used a lot. Now, we talked about combustion reactions at the end of Chemistry 221 in Chapter 7, Part 1. And these combustion reactions always have oxygen as a reactant, and carbon dioxide and water are the products. So we can use all of this to find out then what the initial material was. It's pretty cool.
A combustion reaction of a compound with oxygen forms water and carbon dioxide. The water, represented as blue speckles, is trapped in one chamber, and the carbon dioxide, represented by white speckles, is trapped in a separate chamber. The mass gain of each chamber can be used to calculate the empirical formula of the compound.
The chambers are kind of cool. First of all, the first chamber only absorbs water, and they have special materials that will do that. And the second material only absorbs CO2. So if you weigh, for example, the first chamber before you heated it up, the sample, and then after, the difference will be the grams of water that were collected. And the same thing for the CO2 part. You mass it before and after, the difference will be the grams of CO2 that were absorbed. It's a pretty cool process, actually. This is an example of how this kind of particular thing can work out. In this reaction, we have a combustion analysis. And again, combustion means you've got something organic, which I'm just going to write CXHY for right now. It's being burned in oxygen, O2, and it ends up making CO2 and water. Now, this is a small amount of sample. It's 0.00126 grams of polyethylene, which is something organic, and it yields 0.00394 grams CO2 and 0.00161 grams of water. We can use this information to calculate the empirical formula of the polyethylene. Now, a formula is always mole-based, so if you see gram amounts, you've always got to turn them into moles. Moles of CO2 and moles of carbon are the same. One CO2 creates one carbon. But water has 2 hydrogens per water. So when you're going from moles of water to moles of hydrogen, you've got to multiply by 2, and I'll show you that here in a little bit. So again, grams to moles is the first thing, and then turn them into moles of carbon and moles of hydrogen. So in this problem, 0.00394 grams CO2. Well, carbon dioxide is about 44.01 grams per mole. That allows you to turn grams into moles. And then 1 CO2 had to come from 1 carbon, 1 mole of carbon. We had 8.95 times 10 to the minus 5 moles of carbon. And you do the same thing for water. That really small amount of water divided by the molar mass of water gives you moles of water. And 1 mole of water has 2 moles of hydrogen. So that's where the 2-to-1 ratio comes in. So you end up with 1.79 times 10 to the minus 4 moles of hydrogen. Now, these two numbers are a formula like we talked about in Chem 221, but it's really ugly, like C.0000895H 0.000179. That's too ugly of a formula to do anything. So what you need to do then is compare the ratio. You want to try and find whole numbers. You divide both of those by the smaller number, i.e. divide them both by 10 to the minus 5. And if you do that, then you'll have at least 1 mole of carbon, and you can see how many moles of hydrogen you have. So when you do the bigger number divided by the smaller number, it comes out to be almost perfectly 2-to-1. And the smaller number divided by itself is 1, so that's 1 carbon, 2 hydrogens. Your empirical formula, CH2. So this is another tool of the chemist. If you have something organic, you can burn it, collect the CO2 and water, back calculate the empirical formula, and good to go. Now, you could find the molecular formula if you had the molar mass. We talked about that in Chem 221. We won't talk about that right here, but just remember that's another thing you can do too.